It's like a number group, but 0 and 1. And that's what goes here, and that determines how that.
All right, guys. We'll see about adjusting the lights in a bit.
I did do it on one. I did each step. It wasn't as long.
Okay, so the plan's going to be, we're going to finish up the unit 1 for the test today. Then discuss homework tomorrow. We should have extra time. So if there are questions about any topic, it's in the notes. That's in the other tests. After the homework's been gone over, we should have time for that. Again, homework should come in on paper. Much easier for me to grade that way. And it's probably something that's a lot easier to do with a pencil than electronically, in some cases at least. Then that leaves, that's Wednesday. So Thursday in the afternoon will be our formal test prep day. We'll spend time going over the old tests, whatever stuff we have. Some of those problems are the homework problems. Some of them have already been talked about. We'll talk about a few more until you guys are tired or satisfied, one or the other. And then Friday at 11, we're repurposing for the actual test. It's just, pencil and paper kind of test, so no electronic gear. Okay. All right. I did send back the labs. I didn't get a chance to really make a grading rubric, so you kind of got all the points. So there's not a lot of points because it was just the beginning lab, 10. I do want to make some comments because I did give some of you got these comments back, and I hope you can't see them easily. I don't actually know the student view when you get an assignment back, but that's where I tend to give you individualized feedback if there is any. So, and I wasn't 100% consistent with that. So let me just kind of say what kinds of things I saw. What I think is actually what I'm convinced by looking at this bunch of labs is that it's probably best to put all the important numbers that you want to present into a table. The one that was most often left out, most of you did have a table. The one that was most often left out and left me hunting was the number of runs. So it was, I just noticed that's just, again, so the purpose of writing these reports, I don't think it can't be that different from when you write other kinds of reports for the military, right? Like writing a report in such a way that your reader has to grind through word by word to really get the essence out is probably not the best written report. People want to be able to chop around, kind of see what the important points are, dig in where they need to dig in. And I'm no different. So when I had to that's an important number. So when I had to go through the text to find it, that was much harder than people who put it in the table. So I appreciated that, and that would be a good improvement in the future. And speaking of tables of numbers, also the labels I think could have been a little bit better. Like, for example, this is really a kind of a picky point, but people would have t-test in the table as a label and then a small number. Now, obviously, that number is the p-value for the t-test. Well, because what else can it be? But rather than making the reader infer what it is, it may be better to say p parenthesis t-test, something like that. And so it's a p-value. That's what you meant to say. I think that's right? I didn't misinterpret anybody, I don't think. Other things are that, so your table of numbers also will be less useful if it becomes a dump for a number of stats that you don't actually want to call out in your analysis, in your results, and your conclusions. So for example, skewness and kurtosis, some people put that in the table. I probably came out of a statistical tool used for analyzing it. That's okay, but that kind of adds noise that then covers up the things that you really want your reader to see. Yeah, no one went and gave me an argument about skewness and kurtosis or arriving at conclusions for this level. Okay, if you had, that would be a whole number. I would applaud you if you actually had a point to make about that, and that's why that was there. That would be perfectly appropriate. Okay, so we did cover this in the run-up to the lab, but maybe didn't say enough. So the equal variance t-test is something that it's not sufficient to just say, well, you look at those variances, they're real close. So therefore, I'm entitled to use an equal variance t-test. That really isn't enough. Okay, that has to, when you do the equal variance t-test, underlying that is a strong hypothesis you're making that the variances are equal, that you know it before you even look at the data, right? Now, some things, like, they're generated by a process which is going to give you a bell curve, and it's going to be shifted 1 degree or another, but it's going to be the same bell curve. Okay, that's going to be equal variance. Okay, for sure. But this is not such a case. Or if you think it is, well, that's fine. You got to give an argument for that. That then becomes an unjustified hypothesis, which you need to support in your report. So the easy way out of that is just to say, I don't know if it's equal variance, so I won't use that assumption. And your P's will get a little bit worse, but as you know from this lab, that is not an issue. Easy to get a good p-value. Last thing is that some people gave me a p-value of 0, reported a p-value of 0. Now, granted, it was reported as 0 point and some specific number of zeros, which actually does have a message to it, but that's very rare that people would report. And you would never see that in a published paper, and it probably wouldn't fly in any thesis. So instead of that, what you do, and what most of you did do, is you use scientific notation. If it's some ridiculous number like 1 times 10 to the minus 80 somebody had, okay, then you put it down like that, okay, rather than 0.000 and then say, okay, it's less than 0.01. I get the point, yeah, it's not really a communication issue. It's just a kind of a stylistic issue. Okay, any questions about that? Good. Okay, then let's move. I need to share my screen. Okay. And then once we go live here with the lights, you can tell me if you can actually read it. This projector is quite a bit weaker in my experience. Okay. Okay, now we're on the last slide file for this unit. This is, it shut itself off. Oh, how delightful. So this is the last file. I forget what it's called. It's got game in the title. And so that's what we'll be doing. I think we ought to be able to get all the way through it today. We'll see. And yeah, may or may not be right enough. Too damn, you let me know, and we'll just slow down. Okay. It's not good. All right. Okay. So let's go. Right. So this is game solving. So there's a notion of a game, and you'll see it in the next slide or so, which represents a game as a tree. That's not always a great representation for every game, but it's almost always a possible representation, and certainly for any discrete game, it's a perfectly legitimate representation. The game, in this sense, just basically means so the relevance to simulation is that any conflict is considered a game. A game just means that there's multiple parties, their interests are not necessarily completely aligned. Even if they're partially aligned, that's a game. If there's any element of competition, it's a game. Okay. Right, so we're going to have a state tree, but the actual terminology for the components of the problem are just ever so slightly different from what we've seen in systematic search. So states, that's exactly the same. That would be both the position of the game board. Thinking of simple games. We're just trying to learn the tech here, so I'm not going to stretch my brain trying to bridge over to a real simulation problem. We'll be doing that all summer. So let's say it's something like chess, right? It's not just the board position, because whether it's white's move or black's move says everything, right? Often you could mate if you could move on your opponent's turn, but you can't. You got to wait, and he's probably going to take that opportunity away from you. So it includes both the board position and who is on move, who gets to go next. Okay. So operators, similar terminology. Those are the legal moves a player can make. Okay, instead of a goal test, there's no, I mean, there are goals in a game, but the thing is there's multiple players and they have opposing goals, generally speaking, at least partially opposing. So what we have instead of that are two things. One is a terminal test that just says the game is over or not. It's a Boolean function like the goal test, but it doesn't tell you anything about who wins. It just says this game is over. And then you use your utility function, otherwise known as a payoff function, which returns a number. Okay, sometimes it's like this. If it was chess, +1 white wins, -1 black wins, 0 it was a draw. Okay, if it was something that is a game, is a war game or something like that, more likely we're going to have a continuum of scores. Maybe it goes from -100 to +100. More positive favors one player, more negative favors the other player. Okay, now these are. This kind of a representation is appropriate for the simplest class of games, which is zero-sum games. That means that our interests, if we're both playing the game, are completely opposed, as in chess. If I win, you lose. There's no way we can both win. Okay? All right? So not all games are like that. Okay? For games that are not zero-sum, you have to give separate scores for the min and the max player. Okay, but that goes beyond what this elementary coverage is meant to handle. So we'll assume things are just the easy case, zero sum. If I got +1, then the min player, if I as a max player got a +1, I'm happy because the max player wants the most positive numbers. If you're the min player, you would rather -1. Okay, clear enough? All right. All right, so now we're going to try to solve the game. Now, but it's not completely clear when you say solve a game what exactly you mean. So let me just say that, but there's just two possibilities. Okay, the minimum would be that you are trying to figure out the next optimal move for the player who's on move. Okay, if we're just being short-sighted about it, that's solving the game. And then when it's your move again, you could solve it again to get your next move. Okay. Now, in more complex kinds of game settings, like if it's a partially observed game or there's simultaneous moves going on, that doesn't happen in chess. We take turns, right? But if there's any element of partial observability, then you really don't want to be predictable, because if you're predictable, you're exploitable. Okay, so in that case, the optimal what you expect to get from a solution is more rarely, okay, you must take this action, and more likely you should select from this subset of actions, and here's the probability distribution that you should draw from. You would expect both of those things, including the details of the probability distribution from a solution. Okay. Now, that's the minimum. At maximum, solving a game could mean to figure out the entire game, like figure it out for literally every possible state of the game. And for small games, that's plausible. For something as big as, say, chess, that's really not plausible. Okay. So, but it's possible, right? So what do I mean, figure out the policy for the rest of the game? I mean something like this, not just saying that, okay, in this situation, you should play move X. That was the minimum thing. But saying, okay, and then he's going to go, well, if he goes with Y, then you should respond with Z. Otherwise, you should do W, and continuing on like this to cover all possibilities, all futures. Right? So we're talking about a real big data object here. Okay. Okay, but theoretically possible and even practical for tiny, tiny, tiny games. Not practical for real interesting games. Okay. So there is a state graph, as there was for in the systematic search unit. So here's one for tic-tac-toe, right? You start in the initial state, okay? The max player, so we arbitrarily decided X is going to be the max player. So the +1 result is going to mean that X wins, okay? He's going to go first. You see all 9 possible moves here as children, okay? And then from each one of these, we have 8 possible moves where O makes his mark. Okay. Right. So and then it comes back to the max player to make the next move. Now, obviously, a lot has been deleted from this picture because even for a small game like tic-tac-toe, it's way beyond the ability to put it on a single slide. Even really, really, really tiny, it's incredibly huge. Okay, and yeah, way down at the bottom at differing depths, right? Because you can see this one's going to be at depth 9, right? 9, yeah. This one's going to be at depth 9. This one's going to be at depth 6. This one's going to be at depth 7. Okay, you're going to have some nodes that actually have a score assigned to them because they're terminal nodes. Fair enough. Okay, that's all the apparatus. It's not all that different, but different enough. Definitely has to be talked about. Okay, and here is an algorithm for finding the optimal the value of the state. Okay, that's the way it's phrased. But if you know the value of the state, basically you know who will win, and if you know who will win in the process of determining that, you usually know what the optimal move is going to be. Okay, so so rather than talk through this, I think it's better to look at a picture because this algorithm's simple enough. Okay, there's two forms of the algorithm there. You can kind of take your pick, but let's start off just by contemplating a very, very, very simple game. Okay, so this is the game. So the max player moves first. He picks A1, A2, A3. Depending on what he does, the min player has different options, right? These three or these three or these three, and then we go from there to the score. Okay. Is that clear? Okay, so Evelyn, if I say I'm the max player and I assign you to be the min player, and I say my choice is A3, okay, as the min player, what is the smart choice for your action?
A33.
A33, right? Minimum action. Okay, now, was A3 a smart move? What's the right way to think about this? Maybe I looked at that and I said A3 because I thought, ooh, 14, I'd love to have 14. Okay, so I picked that. Is that solid reasoning? No, because my opponent says, no, you're not going to get 14. You're going to get the one I like the best, right? That's the reasoning that wins in terms of thinking about games. Okay, so what should I have done?
A1.
A1, right? So the one that limits the damage my opponent can do to me the most, right? That's the way it is. And if this was chess, of course, this goes on and on and on, and it becomes very unclear exactly what that optimal move is. All right. Now, to learn the minimax algorithms. This is the simplest possible algorithm. What that algorithm really says is that it's kind of what you think. So let me draw stuff. So it goes like this. When you want to do a minimax evaluation of a node, what it then refers you to is, and from the perspective of max, and it says, okay, then you need to evaluate this node as from the perspective of min, as a subroutine. And then it's going to send me successively to each node there. Okay, to evaluate this from the point of view of min, it says, well, just go down the numbers, and if the new number is smaller than the previous one, accept it. So I would say, okay, this one's 3, not smaller, not smaller. So its value is 3. Okay, so this node up here, before I know anything better, might end up being a 3. Okay, if I pick A1. Okay, but then I have to finish the evaluation, right? So evaluate this again from the point of view of min. So it'd be a 2. 4 is not smaller, not smaller. So we have a 2. Okay, max has a choice of a 3 or a 2. From Max's point of view, the new number is only valuable if it's bigger than what he's already got. He's already got 3. What does he need a 2 for? Not helpful. Okay? Likewise, we go down here, and here now when you have 14, and now min evaluates the next one, 5. Min likes 5 better than 14, so this is the new lucky winner. He likes 2 even better. So the value of this node is 2. Okay, and once again, from Max's perspective, he doesn't care. That's another value. Not better than what he has. Okay, so you see, we just end up taking the whatever the operation is, the min of all these nodes, the min. This is a max node, so it's max over these. It's pretty intuitive, both how to solve it for a test, like on Friday, or how to code it out. But if you need help with your imagination, there are 2 different versions of the text you can look at. Okay, and we could generate some additional practice trees, but we have a harder algorithm to get over, so I'll save it. I'll save it. Save the generator for the harder part. All right. Now, so that's Minimax. That is the basic game solving algorithm. Now, the only problem with it is that we know that trees of depth M have what kind of number of nodes in them? B to the M, exponential with M in the exponent, not very friendly. Then how many of those nodes are we going to need to touch with Minimax? All of them. Yes, there's no option for ever skipping evaluation of a node. Okay, that's what we want to fix next. Because it turns out that we're actually, believe it or not, we wasted a little bit of computation there. That wasn't much computation, but we wasted a little bit of computation. Okay, let's go over, let's do it again in slow-mo and see where I'm doing stuff which is ridiculous. And you could say, whoa, you could stop. You don't need to do that. Okay, right? When we start, we don't know anything. We come down to this one, we don't know anything. I see no option other than being careful here, right? So we have a 3 and a 12 and an 8. The min of those is 3. Okay, this one now has 3. So far, I think we're okay. Okay, now we come down here. And now we see a 2, right? So it's 2. Yes, we can stop. You all see that. Why? Why can we stop?
Because we already found a number that is smaller than the number we already have.
Yes, this number is only going to get, is there any way this number could get bigger with my taking minimums? No. So is there any way it's going to compete with this number for the max player's attention? No way. Okay, so these nodes did not need to be looked at. Okay, and if you come down here, then actually it's 14, and if you have 14, okay, can I skip the evaluation of the other 2? No, because it looks like it might be the best possibility for max, right? Okay, I see. Oh no, it's not 14, it's at best 5. Can I stop? No, because still could be the best. And now, too late, I realize, oh, okay, it's not helpful either. But I can't skip any of those nodes.
Does the act of comparing the number to something higher in the tree take as much computation as looking at a new number?
Generally not. Yeah, generally not. Generally not. Well, you'll see how we optimize around it. Maybe there's more to dig into in your question. Okay. All right, now, so it wasn't a lot of computation to start out with, and yet still some percentage, it's like, 5 to 7% of our computation was wasted. But what you have to realize is that this is most typically a very deep tree. So when you decide, no, I don't need to go down that path, it's not just that node that you're pruning out, it's the whole subtree underneath it, which is also exponential in size. It's not fully b to the m, but it's huge. Okay, so this was realized quite early when I was a kid, and Minimax with what was called alpha beta pruning was introduced. Okay, so that is the last algorithm we need to cover for this test. Okay, let's go. All right, so this is just what we said. Okay, now this algorithm is my Achilles heel. I really hate this algorithm. I just find it confusing. So I'll say this about this concept. For a long time in this class, So normally when I think about alpha beta pruning, I just kind of do it intuitively, the way we just did it on the slide. Like, do I need to keep going? Is there any way this is going to affect the answer? And if you do it that way, and if you're me, you will not get 100% performance on the hardest possible cases, especially if the tree is deeper, but you get 90-something%. So it's a pretty good way of dealing with it. But this is a legit algorithm, so we will go over this next. But if you actually manage to get this into your head, I'm not sure I ever got it successfully into my head. It's maybe not as bad as it looks, but it's got enough that it's not completely trivial. Okay. All right. So the way this is going to work is that alpha beta, what's alpha beta? So alpha beta is the range of scores, of possible scores for a node, which would make it interesting. That would let it affect the computation. As long as it's in between alpha and beta in that closed interval, we should keep computing. But if that interval ever shrinks to 0, then we could stop, or shrinks to a singleton, even we could stop, I believe. Singleton, not true. Like if it's between 2 and 2, I think the algorithm still keeps going in that case. It's still not going to affect the computation, but maybe that's a minor additional optimization that could be made. Doesn't happen all that often. Okay, so that's what the notion of alpha beta is. Okay, but what actually is alpha beta? You know, how do you actually determine what that is for each node in a formal way? That's what this algorithm is meant to do for us. Okay, so right. So what's going to happen is when we're going to call minimax AB for alpha beta on the root of the tree. Okay, and when we start off, we will call this with alpha set to the lowest possible score of any node, any terminal node in my tree, and beta set to the maximum possible score. Now, if it's chess or tic-tac-toe and you use the conventional scheme, that means this will be -1 and that will be +1. If you say, well, I'm not going to tell you what it is, I mean, the scores are some numbers. Okay, then I don't have a choice other than to say, okay, the worst this could be is -infinity, and the highest is positive. Okay, that's what I'll assume for these examples here. Okay, because actually, in all honesty, I don't know what the bounds are on the scores. Okay, it's an abstract game. It's not anything real. So, okay, and now let's look at this. Okay, so if we're lucky and we're being called, and we're going to call this gets called recursively. So once it gets down to the terminal nodes, the answer is easy. It just returns the actual value of that state. Okay, if it's not, then what we're going to do next just depends on whose move it is. If it's a max node, max is going to make the choice at that node. We're going to use this function, figure stuff out, and otherwise we'll use this one, max val versus min val. Okay, we're going to pass in the current value of alpha and beta. Okay, so the behavior of max val is that it takes this interval and it takes the first number, the lower bound, and it will raise it. It can only raise it. It can't, first of all, it can't touch the second number, and it can't lower that first number. It can only raise it. Okay, so that's going to increase the hazard that these numbers are going to cross. I'm going to get a degenerate interval, and I'm going to prune, right? Which is fine by us, right? That's what we like to see. Saves us computation. Okay, so that's the behavior. So we'll start off with a value set to the lowest possible, okay, or max val, which I normally don't try, and that's interesting. I thought I'd mostly learned this algorithm. But yeah, it's actually, I didn't realize that they did that, but okay, that's fine. And then what's going to happen is for each of our children, we're going to want to evaluate them, right? Because we're the max player. We want to know what our options are so we can take the max. Okay, now if this tree is deep, we won't automatically know. If those aren't, terminal nodes, we won't immediately know. So what's going to need to be done is for the children, then we're going to evaluate them. Again, so this assumes that max and min are interleaving, as with chess, as with tic-tac-toe, as with a lot of board games, but not necessarily all games. So just so you know, this is plenty. This is enough to learn. I don't want to make this algorithm any more general than it is. It's still plenty complicated. We will evaluate nodes that are not terminal by min well, it will end up being min. It's going to go back up to minimax, and then it will go down to min. Okay. And then what's the routine going to be? So as we get values coming up from as we get our children evaluated, this will be the value of the node, right? Just like what we were doing when we were looking at the game tree a minute ago. As we got a bigger number, if it's max on move, we'll accept it and take it as the new value of the node. If it's a lower number, we ignore it. Okay, that's what this thing does. It says if that new number is better, that's the new value of the node. Okay? And then what we do is we take alpha and bump it up to be the max of what alpha already is and that value. So if that value is bigger than the alpha that we have, alpha now creeps up as advertised. Okay? This is the case where they've crossed or they've come on top of one another. And actually, okay, in the case when they're on top of one another, we immediately are going to stop computing. So I was wrong, what I just said. We're going to break, and that means we're going to return. Okay, that means we stop evaluating the node, which means that any additional children are pruned, not going to be looked at. Okay, min val is the mirror image of this one. We'll start with the value of positive infinity. Okay, we'll go to each child. We will let the value continue to go down if the values of the children are lower than what we have. We will take the second number, the beta number, and we will lower it according to what that value is. Okay, again, if they cross, we're going to stop and prune. All right. Now, what I should have done, if I was really smart, is printed this out myself to keep me honest. So instead, I didn't do that. Those of you who have laptops up, you can keep the algorithm up on your screen. I'm going to need mine to actually look at game tree. Let's simulate the algorithm because that's what you're going to have. Well, you don't have. You can just do it intuitively, but if you can't do it intuitively, or you'd rather do it in a more robust way, you will want to do what we're going to do next. Okay. Now, there's a step-by-step example here, but it's not quite step-by-step. It still skips things. And so here's a link for an app, which I did not write this one. This is a very smart Berkeley student who went and wrote this one. Again, if you refresh the screen, you're going to get a completely new problem. You can control the branching factor. You can control the depth. You can go nuts. Okay, but this is plenty complicated for me. So if you don't mind, I'll just try to work like this. Okay. Okay. So pointing up means a max node. Pointing down means a min node. Right? It's max, min. Okay. Max, I think starts with what? It starts with minus infinity for the initial value of the node. That's what it said, right? We're now going to call minimax AB on this node, right? And it's going to say if it's terminal, just return the score. It's not terminal. Okay. Then it says do max val, or is it max eval? Come on, guys. What is it? What's the subroutine called for max? Max val. Okay, we need to do max val on the children. Okay, great. So we come down here, right? Okay, so it's a new node. So again, we're going to be back in the top level function, just checking if it's terminal. It's not terminal. It's a min node. Min is playing, so we're going to do min val. So for min val, we take the default score of positive infinity. Okay, and now same story. Okay, we need to evaluate these children. We're going to switch back over to max val. Okay, so we're going to start with minus infinity. We go down to his children. Okay, finally, with numbers. Okay, these are terminal nodes. This one's terminal, so the value of it is 9. Okay, this is max, pointing up, right? So the max of 9 and negative, oh, I forgot the alpha beta, the whole point of this thing. Okay, so to start with, we're going to have the interval be minus infinity to infinity, and then we'll mess with it as it changes. Good. Okay, so now we're going to adjust the value. This is the max player, so you get the worst possible number for free. Okay, now we see, oh, there's an opportunity to get a 9, so we'll take the max of that. Okay, so now it's 9. Okay, this number now creeps up to 9. We check that this interval has not become degenerate, between 9 and infinity. Now this thing, we have a narrower path for this thing to be useful. It's between 9 and infinity. Okay. All right. Next number is 18. Okay, that doesn't affect anything, right? The max of 9 and 18 is just 9. Nothing's going to change over here. Max of 9 and negative 15, not going to change anything either. So we're done. We got a value of 9. We have not proved anything. Okay, 9 gets returned as a value. Okay, min now takes the min of what he has and this number. Okay, he's given the worst option, plus infinity. He'd much rather have 9. Okay, and then this number, I think, comes down to 9. So for this node to be useful, that's our range. Okay, and then we need to go down here and do max of that. Okay, so what gets passed down to him is the current value of alpha beta. So it's minus infinity 9. Okay, so it's going to be more constrained to begin with. Okay, this is a max node, so we'll start at minus infinity. Okay, minus infinity and 1. Okay, so we'll take 1. Okay, this is going to bump up to 1. Oh, now we're tending to be between 1 and 9, so it's getting tighter. Okay, all right. Max of 1 and negative 6 doesn't affect anything. Max of 1 and 11. Okay, 11. Thank you. All right, now you notice this would bump to 11. If we were continuing, this would bump to 11 and it would tell us to stop. Okay, does that make sense? Here's a min node. He already has a 9. An 11 is not interesting. Okay, the code actually is doing the right thing. Okay? Okay, so this actually is not going to make any difference. 11 comes up. 9, min of 9 and 11 is just the 9. Okay, since nothing changes here, nothing changes here either. Okay? All right. And then we need to call max eval on this node. Okay, so starts with negative infinity, gets passed down, negative infinity, 9. All right, let's go. Okay, negative infinity and 10. Okay, this becomes 10. Okay, what do we need to do? Stop. We now have no window for this node to be useful. Okay, that means these nodes will not be looked at and are pruned. Okay, and the number that comes back is never useful. Pruned. All right. Okay, so we finished evaluating this. The value of this node is 9. So says the algorithm. Okay, so that gets propagated to here. He's a max node, negative infinity and 9. He'd rather be 9. Thanks very much. This now creeps up to 9. Okay, he's only interested in things better than 9. That's pretty intuitive. All right, so we go and do min eval here. Okay, 9 infinity, min eval. So, all right, max eval, 9 infinity, starts with negative infinity. Okay, got the boilerplate done. Okay, now we got to do some work. Okay, negative infinity and 19. So this should be 19. Okay, 9 and infinity, right? All right, this is going to creep up to 19. So now we need to be between 19 and infinity. Okay, we got an 18. We got a negative 3. None of them are going to change that number, right? So 19 is the value of this node, so this gets returned. So the min player has a 19 in his pocket, so to speak. This number comes down to 19, right? If it's any greater than 19, the min player doesn't care about it. That's this bound. If it's any lower than I think I've got the other way around. If it's any lower than 9, right, the min player would love it, but the max player is going to reject it. And if it's greater than 19, the max player wouldn't want, yeah, I'm not sure. What I was trying to say is exactly what. Okay, I'll just continue simulating the algorithm. Okay. All right. So now we need to evaluate this node. It is a max node. So we start with minus infinity here. He gets the current bounds, which are pretty strict. Let's see if it makes a difference. Okay. We come down here. Okay, it's 17. So this comes up to 17. Ooh, pretty tight, this window. Okay, doesn't change, doesn't change. Okay, 17 comes up here. This is min between 19 and 17. I'll take 17, thanks very much. I'll bring this down to 17. 17 is a new window. Okay, from here, 9 to 17. Okay, we start off with max node, so negative infinity. Okay, the max here, now it's negative 7. make this 7, right? This, you can only raise this number, right? You can't lower it. So no change there. Okay, this becomes now 6. Okay, we can only raise that number 2. Okay, so the value is 6. This interval never collapsed, so 6 gets returned. Okay, now with the min player, assuming that this would then become 6, even though this interval is still, now I'm confused. Well, let's see. I want to say this should go here. And then this should come down to 6, right? And become degenerate. So say don't do any further computation. But again, it's too late. We've already done all the computation we can. And sure enough, up here, okay, with the max player is going to reject that. He already has the 9. All right, I think we did it right. We'll be able to check it. Just in case. All right, good. We're going to finish at least this one. All right. Again, so we're going to do min eval here. So it starts at plus infinity. The window is 9 to infinity. Oh, wait. Let's see. Yeah, 6 doesn't affect anything up top. Okay, great. We're going to have 9 to infinity over here. This is max eval. Okay. We go up to minus 16. Not bigger than a 9. 6, 7. So it becomes 6, becomes 7. Okay. Nothing ever changed here. Okay. The 7 gets returned. The min player now has a 7. Okay. Which means this comes down to a 7. And what does that mean? It means we're done. We've had precious little pruning here for an example with alpha beta pruning, but that is the end. Okay, the 7 then gets propagated back up. As let's see if I'm right. It should get ignored, right? The 7 is worse than the 9. He's not going to accept it, and it doesn't. Okay. All right. Now the beauty of this is that you can go through now and you can do start animation. You can go through this a bunch of different ways. You can just let it animate under its own speed, or you can go, I like this way, 1 step at a time, right? So you can literally check that you did absolutely every step correctly. Boom, 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 boom. You see it like propagating along here. You can go actually right here to the solution. Oh, look, we got it right. Okay. And then if you just refresh the screen, you got a whole nother problem. All right. So you be the judge. If you want to try to do it intuitively, that's what I do most of the time, but I'm definitely not perfect. And I think if you get this down, then you will be perfect. But it's going to be a little slower. That's the trade-off. Any questions about this? We can do more of this, just not today. We'll have time tomorrow, maybe, or well, it's your guys' time. We're preparing you for the test, so you'll decide.
What we did, but why is the last level is the maximum and then minimum? What is the reason behind it?
Well, because this is a game where the max player is going to make the first move, and then my opponent will make the next move, and then the max player gets to make another move, and then the game's over.
See,
I move, you move, then I move, then we get the score.
between all levels?
Of course, yes. Yeah, it's just a recursive algorithm. It will go as deep as possible, as deep as you need, not infinitely deep. So it needs to be a finite game. All right. All right. So what I want to do next is just talk about some additional stuff that you know. Finish out the unit. There's a lot more to say about game solving. And in fact, there's a lot more that we're going to say, but the more advanced algorithms all use like neural nets and stuff. So we need to talk about that first. So that's why we're going to draw a line here. Let me go back. Okay. All right. So just some conceptual stuff here. Like some extensions. Okay. So the first extension would be evaluation function. So what's an evaluation function? So when I was a kid, like the first chess computers were coming out. All right. And there is no way they were running these algorithms. Alpha beta pruning was known. That was the cutting edge at that point. Okay. But there was no way, even with alpha beta pruning, they were going to get down to terminal nodes with chess, unless you're doing endgame stuff where I got a queen and my king against your king. Okay, it could help you there. All right, so how were they doing it? Well, so what they did is they used an evaluation function, which is a surrogate for the information for it's a heuristic surrogate, a guess, as a replacement for the terminal node information, which would really be the solid information, which you would ideally like to have. Okay? So, in fact, when I was young, chess computers on the side, when I learned how to play chess, people were teaching us as kids evaluation functions. Like, I don't know if you guys did chess or whatever when you were young, but like stuff like, well, here's how you tell who's ahead in a game. Like queen's worth 9 points and a rook is worth this many points. A knight is 3 and a bishop is 3 and a pawn is 1. Sum it all up to see who's ahead. Okay? That is a heuristic evaluation function. It's a guarantee of nothing. You can have a wonderful score and just be on the verge of being checkmated. But all things being equal, it's sensible. It's easy to code. Okay? So the idea is here, you kind of search as deep as you are able to, or as deep as you want to. It probably will not be a terminal node. And then you say, let's treat it like it's a terminal node. Right? Like you basically do a depth limited search, but now you get information from your evaluation function for just any node. Okay, and you can make it more spiffy function than just counting up the queens and counting up the numbers of pieces, a weighted count of the number of pieces. You can start putting in stuff like, well, a queen's worth 9, but if the queen is in the center of the board, then it's really, really strong. So it should be even more. Right? You can start adding other tactical considerations into your evaluation function. Okay. Now, as it turns out, evaluation functions, as a general rule, I mean, this is nothing you can prove, but the closer to the end of a game, when there's less and less going on, the more accurate evaluation functions tend to be. Right? They have less ways to go wrong. Okay, so it still counts to go deep with your search, as deep as you can. Because if the evaluation functions were graded and they weren't any better when you search deeper, why would you waste time digging down in the tree at all? You just look at the children, you do your evaluation function, you say, I'll go here, I'm done. Right? Okay. Right, so that's the story with evaluation functions, and that's what actually made the first chess computers practical. They could actually play a halfway decent game of chess, and that's all they really did. A halfway decent game of chess. Pretty easy to beat them even on their harder modes, and even if you would wait for a long time, give them a lot of compute to dig into the game tree. A typical solution, if you're building a chess computer, or if you're just operating on a budget, right? If this was a tactical model and we're trying to figure something out, we need to make a decision an hour from now, right? We have a wall clock budget of time. So the typical solution is to apply our old friend, iterative deepening, right? The beauty of iterative deepening is if you tell me halfway through the hour that, oh, I don't get the whole hour, we need to act now. With iterative deepening, you will always have a solution in your pocket, right? Because it will do what I just said. It will just go to the child nodes, evaluation function, and within a fraction of a second, it will have an initial recommendation for a move to take. And then if you let it go deeper and deeper and deeper, that initial recommendation should be refined into something better.
If you want to play chess matches and have stockfish turned on, stockfish will give an initial recommendation very quickly. And
Yes.
It doesn't happen very quickly.
Yeah.
Sometimes the recommendation will change after like 4 or 5 seconds.
Yep. Yeah, I know exactly what you mean. Yep, that's what's going on. It dug a little deeper and then said, did I say that was the best move? No. Okay. Other stuff that's interesting. Okay, we talked about iterative deepening. What if our game is not zero sum? Well, then what you do is you got to have a separate number on the terminal nodes for the max player and the min player. You might not even call them max and min at that point. You might as well have them both just try to maximize their score, Okay. So, but not a huge, right? And hopefully you can realize that, okay, you should still be able to make the algorithm work. That's not totally obvious. Go think through how you would modify minimax, how you would modify pruning under that circumstance. What if you got more than one faction, more than two factions, right? What if there's a third faction that's involved in the competition? Okay, no big deal. You're going to definitely need to have one score per player on the terminal nodes so we can do what we need to do. Okay, typically all players would move in a sequence, but it doesn't really matter. Okay, and it's all in all, it doesn't really require anything drastic in terms of the algorithms they give you won't work as written, but it's nothing that drastic. We could figure it out in another hour. Okay, what if the game is random? Okay, chess has no randomness. You know when you take a move, you're going to get to that state. What about if it's backgammon? You roll dice, and that die roll is amazingly powerful, and describing what you can do. What you actually do is random chance becomes a player. So it would be random chance would do their thing. That would be my die roll for backgammon. You roll 2 dice before you do every move. Okay, so random chance gets their move. That tells me what my die roll is. Then I do my move. Maybe I'm the max player. Then you do your roll back to random chance again, and then you take your move. That you have the min player. So it's chance, max player, chance, min player. Okay, and how do you deal with that in the algorithms? Well, it's not really all that bad. There's an algorithm called expectimax as an expected value. That's what it does. So wherever you have a random chance node, you take an expected value. You need to explore all the chains down and take an expected value. But otherwise, it works largely like minimum. Okay. The last thing is just to get you thinking. So when I was a graduate student, was with the first time that a computer was superhuman in chess. That was IBM's Deep Blue. And that was before the age of neural networks were already there. People were working on it, and I was real curious. Are they using neural networks in any way for their thing? They were not using neural networks in Deep Blue. It was mostly a triumph of better hardware, but also of slightly better search techniques. This was one of their main tricks. It's called quiescent search. So I just want to give you the flavor of it, even though I'm late. I'm sorry. But I think it's good to wrap this up nicely. So what they found is when the AI was making mistakes, it was often because of sequences of exchanges in chess. So what I'm talking about is something like this, that my move, I take your knight with my bishop. So I'm 3 points up, right? That's the traditional thing. Those pieces are worth 3. I'm 3 points up. Okay, but it's obvious that you're just going to take my piece back with your pawn. So at the end of the day, it's going to be even, right? So that's the notion here, that you should not try to apply your evaluation function if the scores are fluctuating like that, as they will during exchange. You need to keep going deeper. Okay, maybe you stop everywhere else after some prescribed number of a depth limit that you chose, 10. If we're doing iterative deepening, we just did 9. We're now on depth 10. You'll stop normally at 10, but if you're in the middle of this kind of fluctuation in score, you keep going. You don't stop until the score is stabilized. So what this will mean is, in terms of the exchange, it will wait till the exchange is concluded, and then it will try to decide who's in the lead. Okay. All right. Sorry for being late. We're done for today. If you have questions, welcome to grab me, but you can we'll have time tomorrow. I don't think the homework's going to take an hour to go over.
Would you see in the homework before class starts?
Well, we'll probably do it the other way. Like I said, it's mostly